Solution architecture is the process of designing, describing, and managing the architecture of a specific solution within a business. This involves understanding business requirements, designing a solution that meets these needs, and ensuring that the solution is feasible and sustainable. Here's a comprehensive breakdown of solution architecture and its associated concepts, with real-life examples to help clarify. 1. Introduction to solution architecture. Solution architecture bridges the gap between business problems and technology solutions. It encompasses the practices and techniques to create designs that fulfill specific business needs while aligning with the overarching goals of the organization. 2. Key concepts in solution architecture. A. Requirements gathering. This involves understanding what the business needs. Requirements can be functional, what the system should do, and non-functional, how the system should perform. Functional requirements: features, data processing, user interactions. Non-functional requirements: performance, scalability, security, compliance. Example: a retail company wants to develop an online shopping platform. Functional requirements include user account management, product search, shopping cart, and payment processing. Non-functional requirements might include handling 10,000 concurrent users and ensuring secure transactions. B. Solution design. Designing the solution involves creating a blueprint that details how the requirements will be met. This includes architecture patterns, using established patterns like microservices, client-server, layered architecture. Technology stack, selecting appropriate technologies, programming languages, databases, frameworks. Example, for the online shopping platform, the architecture might be a microservices pattern with services for user management, product catalog, and payment processing. The technology stack might include React.js for the front end, Node.js for the back end, and MongoDB for the database. C. Integration. Integration ensures that different parts of the system and potentially different systems work together seamlessly. APIs, application programming interfaces, allow different systems to communicate. Middleware, software that connects different systems or components. Example, the shopping platform needs to integrate with external payment gateways like PayPal or Stripe using their APIs to process payments. D. Security. Security is critical to protect data and ensure trust. Authentication and authorization, ensuring only authorized users access the system. Data encryption, protecting data in transit and at rest. Example, implementing OAuth 2.0 for user authentication and using SSL/TLS for encrypting data transferred between the user's browser and the server. E. Scalability. Scalability ensures the system can handle growth. Vertical scaling, adding more power to existing machines. Horizontal scaling, adding more machines to handle load. Example, using cloud services like AWS or Azure to auto-scale the shopping platform during high-traffic periods like Black Friday. F. Maintainability and extensibility, ensuring the system can be easily maintained and extended. Modular design, breaking the system into smaller manageable parts. Documentation, clear documentation for developers and users. Example, documenting the API endpoints and creating modular services in the shopping platform so that new features like wishlist or reviews can be added without major changes to the existing system. G. Monitoring and performance. Monitoring ensures the system operates smoothly, and performance tuning ensures it operates efficiently. Logging, keeping records of system activity. Performance metrics, tracking metrics like response time, uptime, and error rates. Example, using tools like Splunk or ELK Stack for logging and monitoring, and employing APM, application performance management, tools like New Relic to monitor and improve the performance of the shopping platform. 3. Real-life use cases. A. E-commerce platform scenario, building an online shopping platform. Requirements: user accounts, product catalog, shopping cart, payment processing, order management. Solution design, microservices architecture, React.js frontend, Node.js backend, MongoDB database. Integration, integrating with payment gateways and shipping services via APIs. Security, implementing SSL/TLS, OAuth 2.0, and PCI DSS compliance for payment processing. Scalability, using AWS auto-scaling and load balancing to handle high traffic. Maintainability, modular design for easy feature additions and updates. using Elk Stack for logging and New Relic for performance monitoring. B. Healthcare Information System. Scenario: developing a system for managing patient records. Requirements: patient registration, appointment scheduling, medical history tracking, secure data sharing. Solution design: layered architecture, Angular frontend, Java Spring Boot backend, PostgreSQL database. Connecting with external lab systems and insurance providers via HL7 FHIR standards. Security: HIPAA compliance, encryption of medical data, role-based access control. Scalability: containerized deployment using Kubernetes for scaling based on demand. Maintainability: clear documentation and modular services for patient management, scheduling, and billing. Monitoring: implementing logging with Elk Stack and performance monitoring with Datadog. Banking system. Scenario: creating a mobile banking application. Requirements: account management, funds transfer, bill payment, transaction history, fraud detection. Solution design: service-oriented architecture, Flutter for cross-platform mobile development, Node.js backend, MySQL database. Integration: APIs for integration with payment networks, credit scoring services, and third-party financial services. Security: multi-factor authentication, data encryption, continuous security audits. Scalability: using cloud-based services for scalability, ensuring the app can handle increased user loads. Maintainability: modular architecture, allowing easy updates to individual services without impacting the whole system. Monitoring: real-time monitoring using tools like Prometheus and Grafana, ensuring the app performs well and is reliable. Conclusion: solution architecture is a critical practice that ensures business needs are met with technology solutions that are scalable, secure, and maintainable. By understanding the core concepts and applying best practices, solution architects can design systems that not only solve current business problems, but are also adaptable to future challenges. Real-life examples across different industries illustrate how these principles are applied to create robust, efficient, and effective solutions.